Hi all, I'm Kasun Wimalasena from Queensland University of Technology and would like to present the paper Assessment of Geogrid Reinforced Weak Subgrade using Modified CBR Mould. So as we all know, weak subgrade is one of the common issue when it's come to the pavement construction, and this condition is very prominent in the state of Queensland, Australia, due to the presence of expansive clay in most part of the state. So to improve the weak subgrade, the soft subgrade, we mainly do methods like construction of a rock blanket, or we increase the granular cover thickness of the road pavement, or we do soil stabilization method, for example, like chemical stabilization. But all of those methods generates the issues of increasing the demand for natural material and increase the construction cost, and also concerns generations on environment, because you increase the demand for the depletion materials, and also mixing chemicals with the soil increase again the environmental concerns and the sustainability. So that's why all over the decades, the geosynthetics have been emerging as one of the prominent method that you can apply to improve the weak subgrades. So geotextiles, geosynthetics comes in different materials like geogrids, geotextiles, and geocells. And a lot of researchers have studied these in terms of reinforcement functions and conveyed that geogrids are the most effective in reinforcing. So we actually use geogrids in this study because we focus on the weak subgrade improvement. By using the geogrids for weak subgrades, we can get the benefits of increasing the subgrade stiffness and increase the pavement overall life cycle, because you reduce the rutting damage and also you reduce the granular material requirement, and hence you extend the pavement life. But this geogrid reinforcement function is not simple. It is affected by a lot of factors: location where you place the geogrid, the aperture size, and the type of geogrid as well. So geogrids are in different types like uniaxial, biaxial, and triaxial. These types also affects. So by looking at the literature, we found that no studies have conducted for geogrids with the road-based materials that are used in Queensland, Australia, because we have a classification called type 2.1, 2.3. For that classification, no studies have been conducted for the geogrids, although they are widely being used in the industry based on the manufacturer specifications. Also, we don't have a simple standard laboratory test that we can do and get the subgrade improvement of capacity of the geogrid. That is again because of the complex behavior. We either have to go for the field studies or do large scale model box testing. So that's why, considering that in mind, for this study, we defined the objective as assess the influence of the biaxial geogrids on weak subgrades to improve under weak subgrade improvement under different granular cover thicknesses. So these are the materials we use. We use clay type soil as a subgrade material, which is classified as high plastic silt. And we use type 2.1 road-based material, which is based on the Queensland Department of Transport and Main Road classification. It is similar to aggregate-based course that we use in Sri Lanka, but here we have a different classification. And these are the properties: the maximum dry density and the optimum moisture content. And as the geogrid, we use biaxial geogrid with 40 kilonewton per meter tensile strength in machine direction and cross machine direction. So we use the CBR test method because that is one of the famous method in assessing the subgrade bearing capacity. But a lot of researchers have actually used the standard CBR test to assess the geogrid reinforcement and found that although you see an improvement, it might not be the real effect because of the significant impact from the boundary condition. And that's why Bergado et al. Proposed a modified CBR mold by increasing the diameter of the CBR mold from 150 to 300 millimeter. Considering that, for this study, for this comparative analysis, we use a cylindrical mold of 300 millimeter diameter and 410 millimeter high, with a plunger size of 61 millimeter diameter and an annular weight of 19.85 kilograms to apply similar surcharge stress, which is similar to the surcharge that we are applying in the standard test. And we load at the rate of 1 millimeter per minute, which is the standard CBR loading rate. So we created test sections by compacting a subgrade to a certain thickness at the bottom of the mold. So subgrade prepared for CBR 4% subgrade by compacting the clayey soil of 44% moisture to a 95% of degree of compaction, actually 95% degree of compaction. That combination was defined based on a lot of trial and errors. And also we prepare the granular by mixing with water to achieve 5% moisture content, which is 2% below the optimum moisture content. With that, we try to eliminate the premature shear failure. So we keep the moisture 2% below the optimum level. And this is the test plan. So we conducted 50 millimeter, 100 millimeter, and 150 millimeter granular cover section. So in this mold, we maintain a total thickness of 410 millimeter. That is the thickness of the pavement section. So we vary the granular cover as 50, 100, and 150. So based on that, we vary the subgrade thickness as well. So for each section, we did a reinforced test and an unreinforcement test for the comparison. For all the tests, we kept the Geogrid at the base subgrade interface. So this is the load versus deformation curves. As you can see, from all the curves, you can see that compared to the subgrade only condition, we can see an improvement in both unreinforced and reinforced sections. So Geogrid has contributed for the improvement, as you can see in the loading curves, except for the 200 millimeter granular cover thickness one, which you can see the unreinforced one has performed much better. So with that, you also can see when you construct a certain granular cover on top of the weak subgrade, you can see it actually helps for the weak subgrade improvement. So when you discuss the weak subgrade improvement by using Geogrid, you have to consider the combined effect, not only the Geogrid effect. So because the granular layer also contributes. For the rest of the analysis, we consider the load to create 5 millimeter penetration to compare the trial sections. And here you can see the load that incurred to create 5 millimeter penetration on each and every case, on each and every test section. So in all sections compared to subgrade only one, you can see an improvement in unreinforced section. You can see an improvement in this reinforced section as well, except for the section has a higher bearing capacity compared to its Geogrid reinforced section. So this is a finding. So this may be due to the formation of a rigid boundary, because studies have confirmed that when you have a Geogrid layer at the interface, you get a stiff layer of granular form around that because of the confinement. So compared to the confined layer, upper part of the granular is still loose, so probably you can get the failure there. So influence of the vertical stress diminishes as you go down to the bottom of the granular layer. So when you have higher granular thicknesses, probably the stress at the interface level is not good enough to trigger the Geogrid effect. For this also accounts that when you have higher granular thicknesses, you need to bring the Geogrid to the top part, not at the interface level. So in order to capture the reinforcement effect, the effect from the reinforcement layer, we calculate the reinforcement ratio. That is the ratio between the load to create 5 millimeter penetration of the reinforcement section to the 50 and 150 millimeter sections. You can see the reinforcement ratio is above 1, means you have a clear millimeter section. So with that, we can say the Geogrid effect diminishes as you increase the granular cover thicknesses, and also it creates a failure early. So with that, we can conclude, despite including a Geogrid, the bearing capacity of the weak subgrade improves due to the thickness of the granular cover to a certain level. So with that, we can see that we need to consider the composite effect, but Geogrid layer definitely contributes for the further improvement. So with that, we can achieve the same improvement by reducing the granular cover thickness while maintaining the same bearing capacity, and the thickness of the stiff layer created by the Geogrid layer is around 100 millimeter. So the future direction of this study is conduct large-scale payment model box testing for the further assessment. So thank you very much, and I would like to answer for the questions if you have any. Thank you.